Hello, I'm Dr Brian Tang. I'm a college lecturer in engineering science at Balliol College.
I'm James Cohen. I'm an associate professor in engineering science and also a tutorial fellow at Balliol College.
And we'll be telling you about the manner in which engineering interviews are conducted here at Oxford. Typically, you'll have an interview with two colleagues from a college, and we'll spend between 30 minutes and an hour, typically, asking you a little bit about yourself, why you want to study engineering, what motivates you, where your interests lie, and then we'll move into the more technical matters where we'll discuss some maths and physics problems. The maths and physics problems that we cover will not extend beyond the things you've dealt with at school. We're not expecting you to have done your own independent research, but they will challenge you. We want to see how you think. So don't worry if you don't know the answer to the questions straight away. That's kind of the idea. And don't believe that we're looking to trick you, because that's simply not true. What we're interested in is how you think and how you approach problems. And what we're really looking for is someone who can take the guidance, think for themselves and apply it themselves, and then can keep going. So it's not a simple matter of getting to the answer, but it turns into a discussion. And the reason for this is the interviews are intended to mimic the tutorial environment. So we're looking to see if you will thrive here at Oxford, and not just whether or not you went to a really good school, for instance. So hopefully you'll see with the demonstration interview that it shouldn't be a scary experience, and a lot of our candidates find that it's actually quite enjoyable.
Welcome to the interview. Before we begin, I just want to confirm, do you prefer Sam or Samuel?
I prefer Sam.
All right, excellent. Nice to meet you, Sam. I'm James Kwan, and this is my colleague.
I'm Brian Tang.
And
lovely to meet you both.
I'm sorry?
Lovely to meet you both.
Nice to meet you. And we will be giving you the interview here at, I guess, in this case, Balliol College. And of course, the structure of this interview is basically we're going to ask a few quick questions about your interest in engineering, and then we'll quickly jump to a math and physics problem. And really just, talk your way through everything, relax a bit. And I'm going to quickly draw your attention to the Miro board that we'll be using. And can you just quickly scribble something for us just to confirm that you are able to connect and you are able to write? Because we will be using this board most of the time. Okay, perfect. So from this point forward, I'm going to erase this, but from this point forward, please do not erase anything on the Miro board. If you make a mistake or you want to, we will cross it out for you because we'll be using a different color, but just keep going on ahead and please do not erase anything. And the other thing is, as one of us are going to be asking the questions, my colleague is going to be writing notes down. So don't pay any attention to that and don't worry about what they may or may not be writing. We'll just focus on the question. So I was looking through your UCAS form and I noticed that you did the unique summer school program. And can you just talk more about that and maybe some of the things that you've learned?
Yes, so I went on the unique summer school program in 2019. It was a hugely valuable experience and a big part of why I ultimately applied to Oxford for engineering. We did a huge range of activities. We had some sample lectures, and we did some practical work, for example, a robotics lab, but also some bridge testing. We did the calculations, then we actually physically built a bridge, and also we had some experience working with the problem sheet style work, which I'm under the impression you get a lot more of when you're at Oxford.
Excellent. And also I noticed that you did some work with, or you enjoy modeling roller coasters. That is not my area of expertise. So could you maybe elaborate a little bit more of that and educate me on what the modeling of roller coasters would entail?
Yes, so what I use is a piece of software called No Limits 2, and it's a fantastic piece of software. It allows you to calculate the G-force read-offs, to render things in very good detail. So it really just allows me to create these very realistic and feasible designs. And I think it got me thinking a lot about real life engineering stuff as well, because as I got more and more experience with this software, I was able to cater to build things that were more accurate and based more closely off of real manufacturers' designs in terms of things like how the elements are shaped and the progression and how I guess you'd orchestrate a ride layout.
And out of curiosity, I know there are sort of these loop-de-loops in roller coasters are very popular, but my understanding is that you can't really build a perfect circle with the loop-de-loop. Is that true, or is there something or?
Originally, a perfectly circular loop was what they used on the first roller coasters, and it was not a big success. One thing that modern roller coasters have that old roller coasters didn't is they have a thing called upstop wheels. So basically, on a modern roller coaster, if it experiences a negative G-force, so the path would essentially be pushing riders upwards. Then instead of just flying off the track, there's the wheels underneath that can keep it conjoined and keep the ride smooth. So nowadays, ironically enough, after going to more like a teardrop shape that keeps the forces a lot steadier throughout the course of a loop, they've now started to experiment with going back to more circular, or even in some cases, more stretched out loops. I think it's very interesting, actually, quite interesting to see how the industry almost flips back and forth on itself.
Well, they always say old is gold, right? So with that, we're going to jump straight into the questions. For myself, I'll be asking you a more of a math problem. So I want you to, at the mirror board, I really would like you to sketch out a certain function for me. So I'm just going to write the function out here. Okay, and if you could for me, just somewhere nearby that plot, what you think this function would look like. But as you're doing so, could you also just talk me through the process of what you are sketching out and drawing our attention to any points of interest that you might think would be relevant for us to look at?
Yeah, sure. So I'm just going to start off by drawing myself a set of axes. Just now, the first curve I'm going to draw is, so we have sine x over x. That's sine x is a sinusoid shape. So on this side, that is 1 full period. And on this side, again, 1 full period, albeit a little off when it comes to the scale. So the next thing is the over x. So that means that as x increases, because we're dividing by x, it's going to be decreasing in magnitude. So 1 over x as just a general kind of curve would look a little something like, well, it would look like this. And there is an asymptote, which I'm just going to try and draw on now, at x is equal to 0, because at this point the value is undefined. The 1 over x does not exist when x equals 0, and as you tend towards infinity, x tends towards 0 from the positive and negative directions respectively. So when you combine these functions together, the point where you have interesting behavior is at the point x is equal to 0. Now, something I learned in further maths is called L'Hopital's rule. And that's basically that the limit of a function, in fact, I'll just change that to an x. The limit of a function as it tends towards a certain value, let's say 0, for sine x over x would be equal to the limit of the function minus cos x over 1, as that tends towards 0. So that's, yeah, L'Hopital's rule is something I would just use without proof. So because in the original one, when we tried to put in 0, sine x of sine 0 is just 0, but sine 0 in the denominator, that's undefined. Whereas with this next one, oh, sorry, I've just realized I've made a sign error there. There we go. Plus cos x, not minus. But with the second one, when we have this, it's going to cos of 0 is just 1 over 1, just equal to 1. So now let's consider back to how this overall curve should look, combining those two things together. So, dear, I'm changing back to the pen. So around 0, obviously we have that rather unusual behavior. So when x is greater than 1, it should be a smaller magnitude than we saw in that sine curve, but when it is less than 1, it should be a bigger magnitude. So what I would expect the curve to be looking like is something to the effect of, it's a little bit more spread out, but something to the effect of this, where as we tend towards infinity, the magnitude just gets smaller and smaller. And on the other side, okay, so sine of x would be negative, but x itself is also negative, so negative divided by negative should be a positive. So I think that it would look more or less like this.
Okay, I think this is a very good start, but I'd like to draw your attention really quickly to this section here. Why would the sine function ever really go above 1? So here you have 1, right? And if you look at your sine x over x, what happens to sine of x as x gets smaller and smaller and smaller? Not necessarily approaching, it's very small, let's just say. So as opposed to practically 0, what would happen to sine of x as it approaches a smaller?
So when x is small, sine x over x is comparable to x over x. So the absolute, okay, yes, yeah, I've drawn this slightly wrong. So basically the maximum value that the function can have is 1. So I'll just move this down. So it would come out looking more like that's our 0, and then again that decaying oscillation. It's a
I'm just going to draw, I'm assuming there's no x-axis on my screen, but this is where you're...
Yeah, I was just adding it. Oh, perfect.
Okay, excellent. That's absolutely right. It's also known as a sinc function, and just in case you've ever come across it. But that's all absolutely right. I guess I could quickly ask you where the zeros are. Where are all the zero crossings? Where would they be?
So the zero crossings are, with the exception of x is equal to 0, which would be on sine x but not sinc x, they're going to be at pi, yeah, pi, 2 pi, 3 pi. So n pi, where n is an integer, but n is non-zero.
Right, greater than 0. Excellent. I think we have time. I'm going to ask another quick curve sketching problem. So here, before we were asking you to sketch out sine x over x, But now I would like you to sketch out x factorial for me. Are you familiar with factorials?
Yes, so factorials would be like, I don't know, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, and so on. Okay. So first things first, I would think about the range over which a factorial is defined. 0 factorial does exist and it's just 1, but -1 factorial is not a valid thing that works. So essentially the lowest, the minimum value on our graph is going to be 1 in terms of the y-axis, and the minimum on the x is going to be 0. So with the factorial function, so like 3 factorial is 1 times 2 times 3, 4 factorial is equal to 1 times 2 times 3 times 4, and so on. Because the thing that you're multiplying by is always getting bigger, I would expect it to always have an increasing gradient. So if I just draw a set of axes for myself, now on the left side, those 2 quadrants, it's just going to be blank. At 0, it's going to be 1. Oh, I did try to draw a straight line there. So 0, 1, it's still just 1. And then after that, I would expect the curve to be going a little like this, where the gradient gets increasingly steeper and steeper.
Okay, excellent. Now, I guess a quick question would be then, it's because you mentioned that factorials typically only work with integers, but really quickly, could you estimate for me what 2.5 factorial would be? Okay,
so the first thing I'd probably do would be jot down, we've already got what 3 factorial is. That is 6, and 2 factorial, just going to add on the side there, is 2. So the factorial function is not linear, so we couldn't just linearly interpolate between these 2 points, as you might often do in a situation like this. So one possible idea I've had, I don't think I know how to make it work for this exact situation, would be just to sort of estimate a curve that would fit this factorial curve approximately, and then substitute 2.5 into that. But obviously, I think that's requiring.
Looking for estimates. So, I mean, even in what you've drawn right here, do you think you could give a rough approximation?
From what I've drawn here, it looks
so
similar.
You said this was 1, and yep. I'm going to assume if this is 2, and then you would have 3, which you said would be 6.
Yeah, so
it's not really scale-ish, right?
In that case, just visually, I probably expect it to be about 3.25 or so.
Sure, exactly. It's as you mentioned earlier, it is nonlinear, so it's not halfway between 2 and 6, yeah. But it's actually slightly closer to 2 than it is to 6. Great. Well, thank you very much, and I'm going to pass over the baton to my colleague Brian.
Okay, now we'll move on to something completely different, so you can forget everything you've just done with James, and we'll start afresh. So now I'm just going to ask you a little question about rolling a marble. So to begin with, I'm just going to give you a slope.
Mm-hmm.
And what we have here is that's supposed to be a straight line, and it's at an angle theta to the horizontal. And onto it, I'm going to place a marble, and that marble is round, even if I can't draw it terribly round. And we'll say that it's a distance L measured along the slope down to where the slope becomes horizontal.
Mm-hmm.
I placed this marble at rest, and let's say it's got a mass M, and then I let go. Could you work out for me how fast the marble will be going at the point it reaches the bottom of the slope, please?
So the first thing I just want to check before we get started, I'm assuming that this marble is quite smooth and the surface it's on is also quite smooth. So is it reasonable to assume that the effects of friction are negligible?
Absolutely, and I apologise. I was supposed to tell you that when giving you the question. We have no friction at all, no friction and no air resistance.
Perfect. So that means because in this situation, the only force acting on the marble is the force of its weight, and that means that in this system, because there's no frictional air resistance, energy is conserved. So energy total is constant. At the top, the marble is at rest. So its initial kinetic energy, I'm going to denote that's KEI, is equal to 0. It's stationary. However, it has gravitational potential energy. Again, we're going to, it's a bit of an assumption, but a reasonable one is that the distance is small enough that we can reasonably take gravity as constant. So GP is equal to mgh. So mg, and the height h is, it's not a very straight line, but the effect is the same, is going to be L sine theta, because L is the distance kind of on that hypotenuse, and sine theta allows us to take the vertical distance. So mgl sine theta. And at the bottom, it's going to have no gravitational potential energy relative to where it started. So set that equal to 0, and its kinetic energy is going to be half mv squared. Now we can equate those two energies as energies conserved. So mgl sine theta is equal to half mv squared. Just going to move this down a bit. And subsequently, we can cancel off some terms. So m, that's present in both. V squared is equal to 2gl sine theta. And v is equal to plus or minus square root 2 gl sine theta. Although I think in this case, we'd probably define, if we're just taking the speed, for example, you just take the positive of those answers.
Good. I was just about to ask you what a negative speed would mean in the context. Okay, that's excellent. So we'll just move on to the next portion. So this ramp that the marble rolls down, I should probably just clarify, because it's not clear on my sketch. At the bottom where it goes horizontal, it's actually a nice smooth join. So it's not an impact, it doesn't bounce, it'll just smoothly exit at that speed you've just calculated. So now I'm going to take a cone, and it's a hollow cone. So picture like an ice cream cone or something. Okay. And what's going to happen, sorry, I should say, this cone has a half angle of alpha, and at a certain height, let's say at a height from the base of big H, the slope that we rolled the ball down is going to feed the marble in, and imagine there's like a little trapdoor here. So the marble comes through the side of the wall, and then it's going to roll around the inside of the cone. Okay, so hopefully you can picture it. I've got just a hollow cone and a marble rolling around on the inside. What I'd like for you to do eventually is to work out for me how high I need to release the marble from initially, so that once the marble goes into the cone, it traverses a perfect horizontal circle. Okay. Now that's a very big question, so perhaps I can give you a hint to get started. And there's our little marble on the inside of the cone, remembering that this angle was alpha. Could you perhaps start by considering the forces acting on it?
Yes. So the first force is going to be the weight of the marble. So that's going to have a value of mg. The next force is going to be the normal reaction force, which is perpendicular to the surface that the marble is sat on. And now I know that this is going to be a question involving centripetal acceleration. So what we're going to want to find is the magnitude of force required that would allow the marble to move in this circular motion. So the centripetal force required for that would be mv squared over r, where v is speed it's traveling at, r is the radius of the circle. So we can find what the value of r should be. Oops, sorry, I'm inadvertently moving myself around. There we go, back to where it should be. So r is going to be equal to h tan alpha, because again it's our height h up to this point and it's an angle alpha. V we can substitute in as our value from a little bit earlier, which was, or rather v squared. That's going to be 2 it's narrow 2gl sine theta.
Was that v or v squared?
That is v squared. Thank you very much. Yeah, you're quite right. So now what I can do is substitute those forces into that formula I've just said earlier as kind of what our desired force should be to achieve that. 2mgl sine theta divided by h tan alpha. That would be our centripetal force. Now, when we look at our marble, actually free body force diagram, the direction we want to take the forces in is normal to the plane. So in the direction that n is acting. So if we can almost like set up our marble's own little axes. X and Y. Now, the next thing you want to do, just so we can work with those axes, is just confirm that this angle here is alpha. You can kind of see it because of how, yeah, you've got that going through perpendicular through the same plane. So the sum of the forces in the y direction is going to, taking again out of the axes as I've drawn them, would be.
Sorry, Sam, could I just interrupt you?
Yep.
Briefly? If we look quite very carefully at this, if I took the angle alpha that I've marked here, that would also be alpha, wouldn't it?
Yes. Yep.
So I think actually you've made a small slip, and that
apologies. So it'd be 90 minus alpha.
Anyway, that's fine. You could now that we've fixed that, perhaps I could perhaps instead we can just draw in a right-angled triangle, and that angle's alpha, and that might be enough. So please carry on.
Okay, so now that we have reconfirmed where alpha should be, so that'll be n, and then because the the weight force acting downwards, mg cos alpha. Okay, so now we've got this far.
So sorry, Sam.
I've gotten the wrong way around.
I think perhaps you're being misled by a drawing that I've made rather too crowded. So perhaps if I just draw above your work a clearer diagram and invite you to take another look. And just remembering that we are looking in the y direction.
Yeah.
As you've labelled it.
Okay, apologies. In that case, it's definitely not cos. So n minus mg, and then we can very clearly see that's the vertical component. Yeah, sine alpha. Yep, that's okay. So now that we have that sum of forces, so we want to equate that with what we obtained earlier as our centripetal force. So that was 2 mgl sine theta over h tan alpha is equal to n minus mg sine alpha. Okay. Now,
Sam, sorry to interrupt you. We're just running out of time. So in the interests of time, I'm not going to ask you to crank through all of the maths, but could you just explain to me down here? So if I, let's see, if I draw a nice big arrow so you can see where I'm pointing, that was your expression for I believe the centripetal force you said it was.
Mm-hmm.
Could I ask you to go back up to the free body diagram and just indicate to me where that centripetal force is?
So the centripetal force I'm trying to recall whether it would act just perfectly horizontal. Yeah, I think it should act just perfectly horizontal to the plane in which it's kind of moving.
Okay, and so can I just get you to draw very clearly one arrow onto that free body diagram to show me where that centripetal force is?
Apologies, can you just repeat that question?
So I just want to be absolutely clear. So could you just draw one arrow onto that free body diagram showing the centripetal force itself? Okay, so you're almost right there. What's the centripetal force do? How do you know there's a centripetal force?
So the centripetal force is what keeps an object in circular motion. What keeps it in circular motion? Now I've said that out loud to myself. I realise that okay, it should be acting in the opposite direction to the direction I've drawn it. It's pushing it towards the centre of the circle.
Yep. Good. So that's going in the wrong direction.
Yeah.
You were heading in, broadly speaking, the right direction. Just down here, in the bottom right-hand corner, if you can see it.
Yep.
This line is.
Yeah, no, that does not work, because if I was equating these forces to be in equilibrium, I should have taken them to be instead of perpendicular to the plane the marble's moving on, I should have been taking them to be horizontal.
Well, so what you could have done was the line above, n minus mg sine alpha was the net force in the direction normal to the surface, but we know that the marble stays on the surface. So I think where you were going with it was you were trying to equate that to 0.
Yeah, and then I could solve for n and take that further on.
But I think you were heading, broadly speaking, in the right direction there. I'm afraid we've run out of time, though. So this concludes the technical part of your interview. So if you have any questions that you'd like to ask us before we close, now's your opportunity, but this does not form part of your assessment. So if you don't have anything that you want to ask, that's fine too.
Yep, I have no particular questions I want to raise.
In which case, thank you for joining us.
And best of luck.
Thank you very much.
Thanks. Well, we just concluded Sam's interview, and we would like to just give some feedback on his performance. And just to get started, we thought that he did an excellent job in sort of describing and discussing the things that he was interested in based on his personal statement. It really did give a sense that he really was interested in engineering beyond just purely the academic sense. I don't know if you've got anything else from that, Brian.
I was particularly impressed that when we started talking about roller coasters, he could actually demonstrate that understanding and the knowledge that backs it up. And that's what really makes me confident that it's genuine interest rather than something he thought might sound good on his personal statement.
Yeah, and although we don't spend too much time clearly on the personal statements, it's those little touches that really, make us realize how interested they are in the topic of engineering. So I guess on to the math questions, which were all about curve sketching. And again, it's not always about, it's not always, every college is going to have different types of questions, so it may not be a curve sketching question. One thing we did want to highlight as part of the feedback was that, it was very evident that that Sam knew a lot more about certain mathematical principles that you may not be aware of, and that's perfectly fine. It's not that much of an issue that you know or don't know L'Hopital's rule or have seen the sine x or over x function or whatever. Those are not really what we're looking for if you could just jump straight in and solve it. But in fact, it's really just his ability to talk about what he's thinking as he's writing it down. That was really what stood out to me as something that was interesting. It was no extra benefit to me that he was able to pull out L'Hopital's rule, but the fact that he could talk about it as he's trying to draw, what he's thinking about as he's doing it, that's quite critical. And you would have noticed that despite knowing L'Hopital's rule, he was still unable to draft the very first sketch on the first go. So that's not a big deal. Very few people are able to, and it's just once you point out, well, what about this? When you probe someone, we probe them, have you thought about this part? The fact that he was immediately able to recognize his error or think about it and come to the correct conclusion from when the mistake was pointed out, that's another good plus, basically being able to take direction or take criticism. And similarly with the factorial problem, he happened to know what 0 factorial was. I mean, if you don't know that, that would not have made any real difference, as you could see in the problem, because ultimately the question was, could you basically draw between the points and infer information, and that's what we were able to see. You could have inferred what 0 factorial would have been, and in theory you could have inferred what 3.5 or 2.5 factorial would have been. And again, it wasn't about exact answers, it was about methods and how he approached the problem. But that was my takeaway from my question of his interview.
On the physics side, on the marble question, I thought Sam actually did pretty well overall. I thought it was very clear the manner in which he was approaching the problems. It seemed to me that the starting point of working out the exit speed looked like a problem that he'd seen before, and that's fine. And he clearly applied sensible reasoning and worked his way through it. What was interesting to me was actually, as we went through the problem and it became more advanced, and he started to make little slips. And one thing I would say is the really little slips, like getting the angle in the wrong place, are really not a big deal for us. It's very easy. What was beneficial was, just as with the maths, when we pointed it out to him, and we try to point mistakes out fairly gently to see if the candidates can work out why we're giving them that hint. He took the information on board and carried on, and that is one of the things that we're really looking for. The other thing was, I guess he got himself a bit confused towards the end, and you could see the nervousness building up. And of course, that will come into play in an interview, but hopefully you could see that actually we're not here to make a candidate feel bad. And what we're trying to do is get the best out of a candidate. I think given a little bit longer time-wise, I've got no doubt that he would have made it through to the end of the question with a couple more nudges. But unfortunately, we just don't have that freedom. We don't have that the time available always. So if you do find, just as we did here, that your interviewer has to end the question before you reach the answer, don't worry. A lot of the time, we don't actually intend every candidate to make it to the end of the question, and that doesn't necessarily reflect on your performance negatively. As I say, I feel that Sam actually did pretty well overall on this question.
And so that's exactly right. So I think Brian and I would have discussed offline and probably would have given Sam pretty high marks and would have considered him moving forward. Now, all that being said, keep in mind that the interview is part of a bigger package overall, and there are many factors that are considered for applicants of whether or not they make it in or not. So really there is context both in the interview itself, but even in the application overall. So don't worry, the interview isn't necessarily, be all end all, but it is, an opportunity for us to get a sense of who you are and how you think and how you approach problems. And really that's at the end of the day, what we do here at Oxford.